Hello, everybody. Good evening and welcome back to Chemistry 161. Oh, what do we got going on tonight? It's late. This is my third class of the day, which is why this class is late. I mean, I don't normally mind late classes, but I have literally been streaming since noon. And now it's 5, and I'm like, oh, I have 2 more hours. Great. Let's talk about a syllabus for the third time. So that's pretty much what we're going to be doing. Where is my syllabus? Oh, I gotta do this thing first. I messed up. You guys didn't get to hear the cool music. There we go. We'll try that. That's better. It's only the third time I've done that today, but that's fine. Welcome to Chem 161. Most of you already know me. I found out earlier that the slide I pilfered this from was outdated. Let's just go like this. Don't worry about this shit. There is no office. There is no White Horse 121. We don't get to go to campus anymore. Who am I? Who's this mysterious voice talking in your ear? My name's Wes Hillman. Most of you had me for 140 because I recognize half your names. If you did not, welcome. Please address me as any of the following. It's literally right down there in the channel name, Professor Wes. So either of those is fine. Wes or Professor, whatever. It doesn't matter to me. The story behind Boss is that a student in an organic class that I taught in like 2011, she's this 67-year-old woman or something like that. She'd been a nurse forever and had to come back and update her credentials or something. So she took my 131 class, and she only addressed me as Boss, and I was like, "Ooh, I kind of like that." So, yeah, you can call me Boss if you want. Mostly the orc shtick is what I do. I played World of Warcraft for a long time when I was just starting to teach, and so I would put orcs over everything, just because I had screenshots from WoW that I thought would spice up like random slides or whatever, and that stuck with me. So either of those is fine. I turned 37 last quarter, so pretty soon I'm gonna have to cross this part out too. I'm gonna be like, I am old or something like that. I don't know, whatever. But it's good to see a bunch of familiar faces. 161 continues from 140 in a bunch of different ways, I guess I should say. We're going to talk a little bit about our schedule and what we're going to be doing and the structure of the class. I mentioned this in the Discord channel, which if you're not in the Discord channel yet, let us know or go to the announcements page on the Canvas website, and you'll be able to get in there. You can talk to everybody. I think everybody stopped talking because I'm there now. So, whatever. There's nothing to talk about. It's the start of the quarter. I'm not going to deceive myself. What do we got? We got the syllabus. Everybody by now, if you're in 161, for sure you know how to use the syllabus. You know how to get to it in Canvas. Let's do this again. Let's see if this screws up like it did before. So this has failed me 2 out of 2 times today. So here's how good Canvas is. I have my password saved because I don't bother typing in my password. So I'm going to hit login. Incorrect password, so I'm not going to change it. I got a pixel. What the hell? That's never happened before. Let's try that again. Wow, there are even more mistakes. I gotta do it again. There. It took me 4 tries to log into Canvas. Isn't that assuring? Like, I don't know what the hell's going on. Although, somebody in an earlier period said Canvas was having issues. As if that was a new thing that never happened before. Pardon me while I resize this. You're getting a 404 error. Did I mistype it? Let me look into that after class. I could have copied and pasted it wrong, or something stupid happened. I don't know. I'll look into that though. If it doesn't get fixed, send me an email. Yeah, if you were trying to get it, I noticed that nobody joined in, and I was like, oh, I guess nobody's checking announcements. This is not the first day of class anyway, but surprise, surprise, is my fault. I might have deleted a character or something. You know what I can do? Let me go find my email. Where is my email? And I will just paste the link. Oh, it worked now. Okay, good. If you have it set up so that Discord captures requests that are directed to it, it'll work. Okay, so if it works, then it works. That's great. Okay, cool. All right, so we're gonna go to the modules tab. Just like in 140 when I taught it, you got to take this orientation quiz. Make sure you do the orientation quiz as soon as you can. I'm gonna fix this link. You guys can't see that this is a link on your page. I'm gonna point our playlist to this link right here. This is the YouTube page that you're familiar with, and then there's the syllabus. You can click on that. There's a bunch of stuff in here. I've done 163 online quite a bit. I even have a bunch of stuff that I don't use here, so you shouldn't be able to see any of this stuff down here. So if it looks like there are a bunch of weird labs and old exams or something, let me know. I will just purge them. So yeah, our class is going to be using an OER textbook, and the OER textbook is linked from each of these pages. Let me find a sample page here. So if you took 140 with me, you're familiar with this, but I have now separated out the individual sections so that they match the slides and they also match the textbook. So for example, if I click here, we're going to talk about the scientific method today. Nothing works at all ever. Wow. Why is nothing working at all? Okay. I'm glad I checked here. Hold on. Ah. I'm just going to pick a different section and see if that's just a random fluke or... Yeah, that one worked. I don't know why the first one didn't work. Huh. Maybe it's just this one. Maybe I mistyped this link. Although... Oh, it is working for you. It's working for me now, too. I'm going to blame Canvas, because why not, right? Okay, yeah, so those links will get you... This is the textbook. So the textbook is online. It's called OpenStax. You're going to see a lot of pictures in my slides pillaged straight from this, because the pictures in this book are actually really good. And the table of contents should be over here. We are doing chapters 1 through 6, but we're not doing them in that order. We're doing chapter 1 and then 2 and then 6 to start. And that's going to be the review. That's going to be the 140 part of the class. So if you've taken 140, most of 1, 2, and 6 is going to be familiar. When we hit chapter 3 and 4 and 5, that's when the new stuff comes up, although there is some in 4 that we did in 140, when we did Lewis structures. That's the general structure of the course, is that we're going to do 1, 2, 6, then 3, 4, 5. The class will be roughly split in half right there. There will be a little bit of 3 on the first exam, so after about 5 weeks, we will have started chapter 3. And then chapter 3 is very, very long. It is the hardest chapter in maybe all of chemistry, 161, 162, 163. Like, it's just weird. And it's weird because it's quantum mechanics. Nobody understands quantum mechanics until you do. That's the wrong page. So that's how you access the textbook. Syllabus is right here. I already have the syllabus popped up. I got to capture the other thing. Let's do window capture 2. And I want you to capture that, and then I want you to turn it on. All right, we don't need any of this Adobe crap. I'm going to just do half of this so I can make it bigger so you can read it. There we go. All right, so if I make this bigger, will it screw up on there? Yeah, it will. Okay. I got to be able to read it too, and it was too small on my screen. Yeah, I messed up. Maybe I can't do it this way. I got to do it this way. Oh, what have I done? I've ruined everything. You know, whatever. I can read it. Okay. So, Chem 161 is, for the most part, going to follow the same rules as Chem 140 with a few minor adjustments just based on the textbook and things like that. So the important stuff to note about this is that if you're taking 161, you hopefully passed Chem 140 with a C or better. If you didn't, you technically don't meet the prerequisites. This class isn't full, so I don't need to enforce prerequisites. That said, I want everybody to be successful in the class and have the best chance of passing. So if you struggled with 140 and got a D or an E or an F or whatever it is that we give you, I strongly recommend that you go take 140 again, just because this class piles on the 140 stuff really, really quickly. So just be mindful of that. The other prerequisites are mostly like general prerequisites. You have to have a strong math background. You have to qualify for pre-calc. And you have to also qualify for English 101. You don't have to have taken those. You have to be qualified for them. Most people probably are already in Calc 1 if they aren't in pre-calc. You've already seen the textbook. That's the textbook. It's online. All those links should work. If you ever see a broken link, let me know. I will fix it. I'm just dreading the day that all the links break, because that's going to be like hours of work for me. As you probably can identify, this is all online. I don't know why you would sign up for an online class if you didn't have the ability to go online, but it does. It's something that I do need to say. You do need to have some sort of method of access to the class, so you might need to have a data plan that allows unlimited data if you're going through your mobile device, or just have like an internet connection through cable or Fios. Whatever you need to do, make sure that you have that before continuing, because you will need to access the internet regularly and for long periods of time. And these videos are up to 2 hours long, and that's a lot of data. I think one of these would wipe out my entire cell plan that I used to have. I used to only have 2 gigs of data a month, and it turns out that that's not very much. Now I have unlimited. What else do we have? I already talked about the OER textbook. You need a calculator. If you have not got a calculator, I'm going to post... Let's see here. Oh, I don't need that window up anyway. That's what that's doing. Okay. I'm just typing it in here. So I'm going to give you the link for Wolfram Alpha. This is the calculator that I use. Online, you can use this. And we'll put this back on top here. Let's do that. There we go. Wolfram Alpha is super useful, and the reason for that is because you could type in whatever you want to in Wolfram Alpha, and it'll try and calculate it. Desmos is also really good. You can get that as an app on your calculator, too. Or, not calculator, I'm sorry. You can get that as an app on your smartphone. I am always just sitting at my computer, so having something that I can type into, like... 14, and then... Oops, I wasn't done, Wolfram. And 4x minus 3y equals -4. I don't know. So I'm just doing a system of equations, and it can just immediately solve that for me. Like, there you go. I plotted both lines. Here's the intersection. This is the solution. Like, that took 2 seconds for it to do. I don't know how to do that in Desmos. I don't know how to do that on paper without actually doing the substitution and then plotting the graph, and like that'd be a 5-minute problem for me. This is actually an equation that you will use in 162 when we give you multiple unknowns with multiple absorbances when we do Beer's law for combined solutions. You can do summative Beer's law. So you are going to be using Algebra 2 stuff. This is actually Algebra 1, I think, but in this class. And having a tool to use that handy is very, very, very important. So make sure that you have access to some sort of calculator. If you have any links or recommendations that you want to pass around, go ahead and send them to me. I'll put them in the chat or on the discussion board or wherever. You put it in Discord. Share that stuff because it's useful. The other thing that is useful is ptable. I'll just type that one in. Excuse me. So that is for a periodic table that is dynamic, and it's just very useful. Having that handy will be relevant for the entire class, pretty much. We're going to use that like crazy. Oh, okay. I've been talking for 5 hours, and my throat's finally starting to get sore, so I got to just keep drinking water. Let's talk about the schedule here. Our schedule is Monday, Tuesday, Wednesday. Monday is our lab day because that's where I put it. We have days off on Monday, and I wanted to just do that. Tuesdays and Wednesdays will be our lecture days. So today, 5 to 7, and then tomorrow, 5 to 7. We'll do lecture content. We'll do chapter 1. And then we'll come back on Monday next week, and we'll talk about lab number 1. I'm going to talk about the lab then. For the most part, when I am streaming, the chat log is available for you to type into. You can do whatever you want to, ask questions to me, ask questions to other students, etc. Just don't be an asshole. If you ask questions that are derogatory or inappropriate in nature of other students or me, I squelch them. If I get to the point where I do that enough and I recognize your name, I ban you. If you are a troll and I ban you, then hooray. If you are a student and I ban you, sucks to be you. Don't let it get to that point. Like, just don't be a jerk and it'll be fine. A student asked me last period, you had to actually ban people? And I'm like, well, I only have ever muted 1 or 2 people, but random people do come into these streams. And I actually had a random person come into the stream asking a chemistry question that was not related to any content that I was doing. I'm like, dude, I'm giving a lecture. I don't have time to answer your question. So he gave my stream a dislike because, of course, that's what people do. I don't give a shit about likes and dislikes. You can like all you want. You can subscribe if you want to, if the notifications help you. You're going to get a lot of those because I have 2 other classes, but all the YouTube bells and whistles, I just don't give a shit. Don't worry about it. Let's talk about attendance. Attendance, I don't care. You are not required to show up to any lecture. It's not that I don't care. I do care if you show up. It's that I don't care to take attendance, and the reason for that is because I don't think it's ethical. There's a lot of stuff going on. Just today, I had somebody email me saying, hey, my lecture time just got moved, and now I can't make your lectures. Can I still be in the class while I lose points? I'm like, no, you're not going to lose points. Like, it's an online class. Just watch the videos later. You'll be fine. I can work with that. But that sort of stuff happens all the time, and I don't think it's right to make people show up at a specific time for something of this nature. So show up whenever you can. If you can't make it, you don't need to email me. If you can't make it, just try and watch the lecture at your earliest convenience. And make sure to ask me questions on anything you don't get, because you won't have that opportunity if you are not here for the live stream. Homework. Let's talk about homework. Your textbook has a lot of practice problems in it, and those practice problems are going to be your source of problems. 161 I don't have worksheets for, and I just don't have enough time to churn them out this quarter, because I have to do that for a different class, and it's eating up all my time. But thankfully, our textbook is really, 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 really good. And it does have recommended practice problems in there for each section. It also has examples. So definitely do those practice problems. The textbook's practice problems are actually a little harder than I think the problems that I would ask are. Um, I like to give that difficulty gauge to students so that they know. Because you always look at a textbook and you're like, are the instructor's questions this hard or are they easier than this? And some textbooks are really like, they give you 2 of the simplest questions ever. And then the next question is like, Bob has 4 apples and gave Sandy 2. Calculate the mass of the sun. And it's like, what the fuck just happened? Like, some textbooks are like that. This one is not really like that. The questions are challenging, and they're a little more challenging than what I will give you on quizzes and exams. So if you can answer those, you'll be able to make it on the test content. Homework is not scored. I do not require you to turn in any assignments for homework. If you have questions about the homework, I'm more than happy to answer them at the lab Q&A. So that'll be on Monday. If you have any homework questions, bring them to be on Mondays. Or send me an email or put a post in the Discord. There's now a channel on the Discord page that specifically is, hey, Wes will answer these questions for you whenever I can. If I hear it ping and I'm at the computer, I'll try and get to it. I'll do what I can to help you there. Email is probably the best way to get to me because I mute the Discord channel while I'm streaming, and that is 6 hours of the day. Quizzes. The quizzes online are just like they were from 140, but the questions are different, obviously, because it's 161. Regarding quiz and exam content and final exam content, so now that most people have taken 140 and you've seen the stuff that you get online, you sort of have a gist of like why all these things are put together how they are, because 140 was a sort of overview, here are the basics class that we're trying to get you to develop the skill set for. Now, in 161, I use the exact same rules that I use in 140, but the content is still more difficult. So we're going to have to be very careful about time management. Now, I know that a complaint that I got last quarter, because a bunch of people mentioned this in the stream, was how the hell am I supposed to answer all these questions with this much time? And the answer to that is if you run out of time, you aren't prepared enough. And I'm just going to straight out say that. If you run out of time on the quizzes, you're not prepared enough. You need to be doing more practice. The reason for that is because I have designed the quizzes so that if you are what I would consider an expert, and the bar for an expert is a lot lower than what you would think. It's you are an A student in 161, you are an expert. If you're an expert, you can answer all the questions in about 15-20 minutes. It still takes time to do the calculations. But what I am trying to prohibit from there being infinite time, for example, is that you go and look up the answer somewhere else, which, as you can see, if you have not been in my class before, I don't restrict you from that. There's a little blurb down at the bottom I got to correct, and someone pointed out. I allow you to use any resource that you want on any assessment you want. So on the exams or the final or the quizzes or whatever, you can look up the answers online. You can look at the text online. You can ask other people questions online. You can use the Discord. I'm not going to stop that stuff. What I am going to do is I'm going to put a giant freaking roadblock in the way that says you have 30 minutes to do this. If you know what you're doing, you won't need 30 minutes. If you don't and start asking for help, that's when the trouble begins, okay? So that's why the time limit is in place, okay? You do have enough time if you know what you're doing, okay? So please keep that in mind. If you're relying on people too much, that's what's going to get you. That's my catch. Just like last quarter, you get 2 attempts for everything. If you have any technical issue that comes up during an attempt, that's what the 2 attempts are for. I cannot give you extra attempts for any other reason, for equity reasons. I got to make sure everybody has the same opportunity to use the software and also to be successful. If you have an issue and you think it might be your internet or something like that, generally speaking, don't take both of your attempts at the same time. Like if your computer dies, maybe take the next attempt tomorrow or something. I mean, you're going to be stressed out from that anyway. That said, please let me know. In extreme circumstances, I can work with you. But for the most part, I do not grant additional attempts for any reason. A change that has been made to how I do online stuff. After you finish your assessment, so quiz, exam, final, you do not get your key. You also do not get a score. You will be required to use your own judgment in order to determine, should I take the quiz again. You get 2 attempts. If you do the first attempt and you feel like you did it poorly, yeah, take it a second time. I keep the better of your scores. But I don't show you your score anymore. So the reason for that is just it added an extra layer of complexity on my end. Like, there's all these toggles that I have to hit, and setting it up this way means I push one button. So it is entirely convenience, but I was able to justify that with, in real life, air quotes, if we were in the classroom, you would turn in your quiz and then I would take it to my office to grade it, and you don't get to know your score until I hand it back anyway. So it's similar enough to that I was like, yeah, I can justify this without accidentally having to toggle one of these other buttons that who knows if Canvas will even do it right, because it can't even log me in, right? So that is a change that has been made. So just be mindful of that. When you finish your quiz, it will just say the quiz is done. Congratulations. The exception to that is the orientation quiz, which does show you your wrong answers and so on and so forth. Exams are just like quizzes, except they are more content and they are longer. I give you 75 minutes for an exam, and I give you 120 minutes for the final exam. If there's any questions about assessment besides laboratory, which we're going to talk about on Monday, let me know. This is the part where I give you like a minute of awkward silence to type anything in the chat, because the time it takes for my voice to get to your speaker and then your text to get back to me is a little bit. So I'll give you a second to do that and see why somebody is texting me over and over and over about crockpots. I have a friend who, he's also a chemistry professor, and he just, I tell him like, hey, here are the times that I stream. Don't message me during that time. So when does he message me? Only during those times. Just specifically during my lecture time. So it's like, for fuck's sake, Brandon, stop it. I'm turning my phone upside down, and he just messaged me again. So I can't turn my phone upside down. I need to know when break time is so I don't talk for an hour and a half and you guys don't get a break. Let's talk about the lab very briefly, just as far as the schedule is concerned. We're going to do lab every other week. There are 5 labs. The first lab is week 2. We'll start on it on Monday. Any Monday on the syllabus that is marked Q&A is going to just be review. We don't lecture on Monday unless I have to and we fall behind. 161, there is a chance that I can fall behind. There is a lot of content, but once we can get through most of Chapter 3, it starts to cruise. Chapter 3 is the real mud of the quarter. The late work policy has not changed from 140. If you are turning in something after a hard deadline, I don't accept it. If you turn in something before or after a soft deadline, I accept it as on time. There will always be a soft deadline posted for a quiz or a lab. For an exam or a final, the hard deadline is all you get, because the hard deadline is the last day of the deadline. I will communicate those deadlines by posting them on Canvas and also making announcements that say last call. The last call announcement, it says 1 hour in the syllabus, but I have pretty much accepted that I just set the deadline as 11:59 p.m. the day I make last call. So make sure you get information in by the soft deadline, and if you absolutely can't, get it in by the hard deadline. The last little caveat to that is, if you miss one assignment for any reason, you can use this NQA coupon, we'll call it, to get a opportunity to turn it in. So if you miss a quiz, you can do the quiz later. If you miss a lab report, you turn in whenever you can. You just have to claim it as NQA, and then I mark it in the gradebook. You get 1 NQA. If you take a second NQA, I zero your grade. I actually give you a failing score in the class because that's academic dishonesty. So don't abuse that. But do remember that it exists. Because if you don't use it, it's not worth anything at the end. Here are the points that are in the class. There are a few more points in 161 because the quizzes are lower in number but are worth more. This is because there are only 6 units in 161, so I only give you 6 quizzes as opposed to 9. Each of those quizzes is worth 25 now instead of 10. So the stakes are higher, but you have more varied questions. And also, a lot of the questions that you're going to get later on in the quarter are going to be of like a multiple choice variety or a choose this answer from the thing. There is a point in 161 where we put the calculator away and we don't take it out again. That is chapter 3. There's one problem type in chapter 3 that we do, and then from that point on, the calculator is done. It's all word problems and just conceptual stuff. So the first few quizzes will have a lot of calculations, and there will just be problems that are worth like 4 points or whatever. But then you're just going to get a bunch of rapid fire, true, false, explain this, or arrange these from lowest to highest sort of questions. And that's the sort of stuff that you see in the orientation quiz, and so far as question types are concerned. Because the class is a little harder, I do scale up the percentage. You need to get 73% of the points instead of 72 for 161, and 93% of the points to get an A. That generally doesn't affect things in terms of how many people get what grades, because the number of people that I get A's in whatever class tends to remain constant. So if you did well in 140, I expect the same from you in this class, unless something tragic occurs. And that can happen. I'm not going to say that you're a shoe-in for an A if you got an A in 140, but for the most part, my data seems to support that people who are strong in 140 will do fine in 161, even though half of the content is very different. And I would attribute a large percentage of that to just like work discipline and strategy, I would say. So like if you pin down times during the week that you're going to work on the content for this class, and you get in a consistent pattern of I do this, then I do this, and I do this, you'll be prepared. This class is deceptive, but there's a lot of really simple details that lurk under the surface of quantum mechanics and stuff, and I will do my best to try and explain those to you in that way of like, hey, this is all you need to know, and then everything branches out from this. So total points of the class are about 550, 575, something like that. It's right here, 575. You can calculate your grade at any point by figuring out the number of points you have earned divided by the total number of points possible, and then multiplying it by 100%. There is no extra credit other than the exams in the final, where I give a few extra points if you get a perfect score. You do not need to get 100% of the questions right in order to get 100% on the exam. So if you missed 8 points on an exam, you'd still get 75 out of 75. There's just more points than are possible. Canvas can't deal with that, so I have issues with grades. So around that point in the quarter when we have an exam, your grade will start to differ from what it actually is. With your permission, I will email you your grade, or at least the row that I have in the grade book. But other than that, Canvas will approximate your grade. Try really hard not to worry about your grade in this class, because grades go all over the place, especially early on. If you need anything regraded, let me know. Canvas questions are quirky, and if you see something that, like, oh, this is obviously wrong, like the key is an error in it, and I didn't get points for it, let me know, because that will be affecting other students. I will fix that. If you are asking me, can I get more points or partial credit on this because Canvas did this function, like I got 4 out of 6 right, correct, and it marked me wrong and gave me 0 out of 1, no, I won't correct those. So just be mindful that some problems are purposely set to test you on some sort of learning objective, And if it is one of the question types that zeroes your score because you made an error, then I can't help you, unfortunately. That's a problem with Canvas, and I hate it. But don't worry, because at the end of the quarter, all of the scores are normalized anyway. I don't curve scores on the class. You are graded entirely on your own merit. Somebody asked me last period how many people out of 100 got an A in 140, and they expected the answer to be like 4, and I think the answer was 25. So it is possible for a quarter of the class to get an A. It is possible for all of the students in the class to get an A. I don't curve scores at all. It's entirely your own merit. And I do tend at the end of the quarter to add points to the class based on perceived difficulty and then issues with Canvas. So if you want to know what your grade is to a high level of detail, email me, but only at the very end of the quarter, because in the meantime, Canvas will be good enough. If you have a CDS information that I need or any documentation, please get that to me as soon as possible so I can set Canvas up to accommodate you. This policy right here, somebody pointed out somewhere, I forget where I was given this information, that the policy seems to have changed. I didn't copy and paste the other thing onto this, so this is my in-person academic honesty policy. You're online, and I don't think it's realistic of me to expect that you don't help each other in some way, and inadvertently that may spill over into exam stuff. So, for example, let's suppose your friend asks you a question and you answer it, but you didn't know they were taking the exam. According to this, like, you would be in violation and be expelled. Like, that's not cool. Like, obviously, I can't enforce that. So, as written, the academic honesty policy on the syllabus right now is kind of garbo. If you were giving information to another student during the exam in person, then yes, I could easily enforce that. But in an online environment, there is no way for me to discern, or for you to discern, what the intent or activity of the other person on the other end of the line is. So ignore the academic honesty policy. The only thing I care about is that if you are submitting something to me, that it does not have identical content as somebody else with your name on it. For example, if I get 2 lab reports, this happened to 2 students a few quarters ago. They sent me the same lab report, and there was a claim that an issue came up with uploading, and I was required to zero the score because of the campus academic policy. And that's not a situation that I wish upon anybody. But I am bound to this policy as much as you are because it's campus wide. And so there is a thing about plagiarism. If you submit 2 papers with two papers that are identical and have different names on them, I can't discern who did the work, and I can't give credit to them. So that's the big no-no. Don't pass your lab report over Discord to somebody else and then upload it with your name on it, because that'll get flagged. You are absolutely allowed to work on Google Sheets together, but I would strongly recommend that you work on your own Google Sheets so that you have everything in your own handwriting. But if you have them side by side and then are talking to each other, that's totally okay. That's called research, for what it's worth. And I encourage you to work together and to use other classmates as resources so that you all benefit from it. Use me as well as a resource. I can't answer questions directly, and I can't participate on anything quiz, exam, or final related. But I will do my damnedest to point you in the right direction and then just give you a firm shove so that you the answer's in front of you, and then I will push you into it. So that I didn't tell you the answer, but you found it. So that's sort of my ethical stance is I will try and do everything I can without telling you the answer. And then finally, you're responsible for your own learning experience. So make sure that you're putting in the effort that you want to get out of this class. If you don't put much into it and then you're like, man, this class is just kind of exists, whatever, then yeah, you get more out of stuff the more effort that you put in. And learning this level of chemistry, this is effectively AP chemistry. that we're doing now requires both practice and effort and commitment. And if you want to make it there, you can. You just need to put in the time. That's really what's going to prevent a lot of people is I don't have enough time. This is a 5.5 credit class, which means that roughly every week you should be spending about 10 or so hours on work outside of the lectures. So make sure that you are doing that. There's our schedule. I got to make the schedule fit on the entire screen, so give me a second. The deadlines are shown on the schedule for many things. You'll notice that labs are due on Tuesdays because they are assigned on Mondays. You get 1 week and about a day. The deadlines that are listed are soft deadlines. For the labs in bold, they are hard deadlines for the exams and the final. Note that the exams are on Fridays this quarter because our classes are Monday, Tuesday, Wednesday. So if you were expecting an exam to be like a weekend after, that would be a rude surprise. So just note that. And I will also let you know that, like, hey, this is when our lectures are. Or not lectures, I'm sorry. This is when our exams are. All right, that's the syllabus. Let me know if you have any questions about it at any time. All right, the last thing that we're going to talk about before we take a break, study strategies and habits of students that are successful in this class. We have collected data on this. In fact, I even have data from today that students talked to me and said, like, hey, what can we do to be successful? And then they brought up these points independently, like before I even brought the slide up. So how are you successful in this class? The first thing that you should probably do is read the textbook before lecture. Write down anything that you think is important. Write down some notes. Write down questions. Anything that seems unclear or confusing. That's a great place to start, because then when you come to lecture and we talk about everything, I will clarify those points. And if there's anything you still don't know, then I can answer that question for you. Not everything in the textbook is something that I will cover, mostly because of time constraints or complexity issues, or I don't feel the textbook goes over it well enough. I will note to you when those instances occur. After your lecture has been completed, you'll want to do practice exercises either by yourself or with other people. It's really, really important that... I just wanted to click on this because it wasn't moving. It's really, really important that you practice this class regularly, because there's going to be a lot of content coming at you really fast, mostly on the premise that you've seen it before, because you have. That was 140, or high school chemistry, or etc. And then finally, make sure to ask me questions. Use all the resources at your disposal. So you can ask me questions over Discord. You can ask me questions over email. You can ask me on the campus, the Canvas discussion boards. You can ask me questions on the chat log during class. Any of that. I am the person that is assigned to answer your questions. If you don't ask me questions, I feel like you're not getting your money's worth out of the class. So don't ever feel like, oh, I asked you so many questions. It's literally my job. They are giving me money so that I may live and buy seltzer water, which is my new addiction now. I've drank 4 cans of seltzer water today. And buy food and rent. Like, they are literally funding my existence so I can answer questions. It seems weird not to ask me questions. So please do. And then the last slide is just 2 hours a day. You probably know that by now if this is not your first science class. If it is, you do need to put effort into this to get a C. Putting more effort into it will get you an A. Hard work does pay off. You do not become an expert, just like you would not become an Olympic gold medalist by watching Usain Bolt run the 100-meter dash 3 times. Like, that doesn't make you an expert. Gotta do the practice yourself. I was really struggling to think of an athlete in the Olympics. So I was like, who's the guy with the world record? Bolt something. Crap. I know he's really fast. That's it. Popular culture is something that I'm not very good at. That's the first hour. So the second hour, we're going to do chapter 1. But because it's a 2-hour class and I don't expect anyone to sit here for more than an hour at a time, we take a break. Let me hit a button here so I can set this up. I'm just going to get the next slide set up real quick. But the break is for 10 minutes. Where are my slides? I got to find them again. During those 10 minutes, I start a timer. If you are wandering around your house or apartment or whatever, and you see that the screen looks relatively like this with the timer in the middle, we're still on break. Keep taking your break. If you return and it looks like this... Oops, hold on. If you return and it looks more like the slides are up, that means to come back. That's the title card. I gotta go to this one. So I'm going to hit this button right here. That should have worked, but I didn't. I had it minimized. I'm going to turn on the music once again. And I will see you in 10 minutes. Will I get another 10 minutes flat? I got one last quarter. I don't expect to get it again until like the very end. Alright, I'll see you in a bit. Close enough, right? Always have to stop on Zelda's Lullaby. That's too bad. There we go. Let's see here. Boop. I made fun of my friend during the break. He has literally messaged me how many times? Let's see here. 14 messages today, and the first one was the minute I started teaching today. And the last time he messaged me was on New Year's at midnight. After I messaged him back. So I was like, for fuck's sake, dude. I told you I'm teaching. Alright. So I had to publicly lambast him because he'll laugh about it. And then he'll feel bad, but then he'll laugh about it again. Chapter 1's a review. Chapter 1 is all about the basics of science in chemistry and how we are going to do the scientific method, as well as some qualitative categorization and some quantitative methods that we're going to use. So there's not very much here that is going to be new from 140, but there will be little bits and pieces that I will point out, and those will be essential to understanding, because the whole point of 140 is to give you the groundwork for 161, 162, 163, but we don't give you the entire story in 140 because there's just not enough time. So here we go. So let's talk about what chemistry is. Chemistry is the study of how matter interacts when it interacts with other matter. So does it react or does it not? And we've been doing this for a very long time. So a long, long time ago, like over 4,000 years ago, everybody thought that all of the matter around them in the universe was comprised of 4 elements, and those 4 elements were air, water, fire, and earth. There was a 5th element, that's Leela, but that came in 1997. So the ancient Greeks didn't find out about her. But they thought that these 4 primal forces were what made up matter. And they had no real way to figure this out other than thought experiments, which we're going to talk about Greek philosophy and why it's stupid in chapter 2. But we literally started here. We started with the making of a role-playing game. Air, earth, water, and fire. That was our periodic table. That's why they're called elements in video games, is because that's where this term came from. Around the like 13, 14, 15, 16th century or so, we had the Renaissance. And during the Renaissance, what happened was there was this giant boom in inquiry of science. And what people started to do were things like basic study of matter in the world around them. So like, okay, I have this mineral. What are its properties? Can I turn it into something else useful? This is where the whole alchemy idea came from. Alchemy is baby chemistry, basically. Like, it's where chemistry started. And it is actually a science. It's just that a lot of the goals in alchemy weren't feasible. For example, the most famous alchemical experiment was, how do I turn lead into gold? And it turns out that you can absolutely do that. It requires a nuclear super collider and a whole lot of energy, and the amount of gold that you make is so small that it would cost you more to operate this device than the value of the gold you've made. So it's not practical. You can do it, though. You just need to hit something with enough force that you knock a helium nuclei out of it. 2 of them, actually. And then it has to capture an electron. No, it doesn't have to capture it. It has to undergo electron emission or something like that. It has to go under beta radiation. Something like that. I have to sit down and work it out, but it's a whole long, involved process, and it takes a lot of effort. There was no way these guys that were in this painting were going to be able to do that in 1580. This is the Kovacs lab where I worked next to, I should say, in 2002 to 2005 was when I... No, that's wrong. I'm sorry. 2006 to 2009 was when I worked at UW. I worked in the Goldberg lab, but the Kovacs lab was next door, and this is a picture I found of it. So you could see that the science has gotten progressively more and more complex as our understanding of it has improved. With the exception, of course, of Leela, who I think is the most complex, because the fifth element was made in it was set in a much later time period. So, but the gist is that as we develop science and we understand more things, we build upon our knowledge to discover even more things. And then we build upon that to get even more things still. So chemistry is going to be a science that builds upon its foundation. And we're going to take that foundation from 140 and expand it here. And then we're going to use that chemistry to explore all sorts of other things. If I am not mistaken, most people who are in this class are here because of these reasons. That's probably good. If you are in biology, you need to take chemistry because biochemistry dictates how things like enzymes and proteins and lipids work in a cell. And the cell is important to understand because how a cell behaves would help us understand how like viruses infect it and stuff like that. Medicine, for the same reason, like you need to know what the shape of a molecule is in order to understand how it interacts with enzymes so that you can use it as a treatment. The wrong shape of a molecule can be disastrous. I keep forgetting what this is called. I'm gonna have to type it in really quickly, but it is a molecule where if you flip it around and you get a different shape, like it's a mirror image. Enantiomer. I think it's thalidomide. There we go. So there are two different ways to construct thalidomide, and they're mirror images of each other. We won't talk about chirality in this class very much until maybe chapter 4, just as an example. But one version was it suppressed like pregnancy issues. So like upset stomach, morning sickness, pain, that sort of thing. It suppressed those, and it was basically like a analgesic sort of thing. But the other variant of it, the other form of the molecule, caused severe birth defects, including babies being born without ears, eyes, or arms. And those are very important things to have as a baby. So, it's important to understand why that happens, and chemistry helps that too. And then, of course, material science and engineering, you're going to build shit. You don't want to build shit out of sodium because it'll blow up. There's a reason we don't make planes out of magnesium. That reason is the Titanic. That just lit up like a signal fire, right? Not the Titanic, I'm sorry, the Hindenburg. The Hindenburg and the Titanic were both bad ideas, so. Alright. Everything around you involves chemistry in some way. Here are just some examples that I've put up there. But the point of these classes that you're going to be taking, from 161 all the way through 263, if you are going that far, if you're going that far, you're biology. Congratulations. The whole point of this is to understand how the stuff that we're going to throw at you behaves, and how you can use that information to predict what it will do with other matter or other circumstances, and how you get the most out of it. It's all about pattern recognition. It's all about understanding concepts and linking them together. And there is a little bit of quantitative analysis too. So we need to be able to do calculations and do dimensional analysis. Fortunately, until you get to either 163 or 361, it's all algebra. We can do some calculus when we talk about kinetics, but we don't need to. So that's the approach that we're going to take. So let's talk about the philosophy behind how we do the scientific method. So how do we figure out science? Like, what's the order of operations here? And that order of operations is, hey, I get some idea. We're going to start here. And when you get your idea, from that, you're going to make a hypothesis. So we'll just indicate that here. So once I have the idea may have come from some sort of observation that was made. So, for example, you might be looking at something and wondering, how does this work? Like, by what mechanism does this leaf grow? Like, how do plants thrive? Like, you might look at that and be like, okay, well, the plants seem to thrive in sunlight. If they're in the shade, they don't. So that would be an observation that you'd make. And from your observation, you'd get your hypothesis. So you would have to do an experiment based on the hypothesis that you make. And your hypothesis will be based on some information that you have. That information comes from your observations. So using our plant example, you might say, okay, well, what if I put a plant in like a dark room and a plant outside? I'm going to test to see if sunlight is what makes them grow, or if it's just water and they happen to be outside. Then the next thing you're going to do is the experiment. Once you have figured out your data and you've set it up your idea, you do the experiment. The experiment in this case would be, okay, I'm going to plant 2 plants. They're going to have the same size pot. I'm going to give them the same amount of water. They're going to be the same flower. I'm going to try and control everything that I can to be the same other than the thing I'm testing for. Which in this case would be, I want light for this one and I don't want light for this one. And that's more or less the gist of it. After your experiment is done, you're going to get observations and data out of that, and you're going to get results that will either be consistent with what you expected in your hypothesis or inconsistent. If your results are consistent, then you can do further tests. The cycle repeats. What ends up happening here is that if you do something in an experiment and you discover a result, and you can do that multiple times, you need to be able to reproduce it or it's not a result. We're going to accept it as fact. That's a scientific fact. You might remember scientific fact law and theory from 140. And this is more or less a better diagram of how that works. So once you have a scientific fact, because you've done an experiment and reproduced the data and got the same results so that you could say, oh, this is what happens, you can then use those facts to try and discern laws. Laws are properties that apply to a general idea here. So, for instance, our scientific fact might be that a daisy cannot grow in a darkened closet because it needs light to live. The scientific law would be plants in general need light to live. So we've expanded that into a bigger category. A fact is very specific. It's for one experiment, whereas a law is just a general observation that combines all of those experiments together into a statement. Now, why do plants need light? Does the observation that I lock them in the closet explain what's going on there? No, it does not do that. It only tells us that light is essential, but it does not tell us why. What I like to use is that we say that scientific laws describe how matter behaves. This is the observation, and we describe it from the conditions, but we don't know the underlying reason. If we do know the underlying reason, then we know why it does this. So this is the difference between how and why, and this is a very important distinction that takes a while to actually understand as a student. I didn't think that I thought how and why were synonymous for the longest time. You just use whatever. But it's actually used in a very specific context. If you understand why the light is important, then you can ascribe a scientific theory. Our why in this case would be that light is absorbed by chlorophyll. That light is used to move electrons along the electron transport chain, which eventually is used to synthesize glucose from carbon dioxide and water. So if you don't have light, the plant will absorb CO2 and H2O from its roots and also its leaves. But then there isn't any energy to combine those two things into glucose, which is the energy that is used to construct cell walls, as well as a carbohydrate that can be consumed to provide ATP. Without doing a lot of experiments, you could not tell that by putting a plant in a room and then turning out the light. So we have to go sort of in this order. We have to get the facts first, and if we do enough experiments, we can get a law. And if we do different experiments, we can get a theory. This is why the law and the theory are sort of branched out into two different areas, because they're not exactly the same thing, but one definitely helps support the other. Now, if you hear the phrase, it's just a theory, let me write that down really quickly. So if you hear, it's just a theory, ever uttered by somebody, you have my permission to kick them, because a theory is extremely important for science, okay? And anybody who says that doesn't understand science. They are dumb. So, you have my permission to tell them that they are not being scientifically accurate. Please just don't tell that guy who does the game theory stuff, because if he finds me, I'm in trouble. I've been making fun of him every quarter since I started teaching. But what do I know? He's probably making millions of dollars on YouTube from, like, sponsorships and whatever, and here I am just teaching chemistry. So, who's the dumb one? I guess I'll never know. But the point is of that joke, and the whole point of the joke is so that you remember, a theory is really important. A theory tells us exactly what's going on to the best of our knowledge. Alright, let's do the sodium experiment. If you were in 140, you saw this. What we're going to do is we're going to look at some scientific facts and see if we can draw some conclusions here. So let me push this button. This screen will come up, and then I need to capture it again. That is not the one I want. There it is. Boop. Okay, we don't need any of the recommended stuff. We just need the video. Alright, so what we're going to do, I'm going to take 3 videos here. These are all reacting sodium with water, and our job is to observe what happens here. So let's see if we can figure out any trend. And this goes on forever, basically. There we go. So what trend did we observe? Hint, it's on the screen right now. What could sodium do with water? Now, a much better question would be, does this happen every time in every possible configuration of sodium and water? And so in order to answer that question, we would have to cut different chunks of sodium, use different amounts of water, and try and explore those sorts of things. So I've attempted to reproduce that by getting you 3 very different videos of sodium plus water. So let me get video 2 out here. Video 2 is very professional. It's so professional that they warned me that this video may not be appropriate.
Disgusting. Disgusting.
So there's their sodium, and they just chuck it in the water bucket.
You doofus.
Yeah, no, it's floaties.
The longer it takes, the farther back to get. It takes a
Gee!
Very professional. Now, as you can see with their very scientific approach of using a butter knife on a stump, I mean, they're at least wearing gloves, thankfully.
Boom.
What scientific fact do we still nevertheless observe? I thought I was going to pause it on the... I'm trying to pause it on the second one. Oh, there is one. That's okay. We still notice that the sodium metal explodes. So that's convincing enough that one of these was sort of scientific. I mean, it was a guy throwing water into, or throwing sodium into water. and then running away from it. This was just people cutting sodium on a stump in the wilderness. This one's going to be much more scientifically minded. This is a scientist who is taking a chunk of sodium, which you can see right here, putting it on water. This thing that you see right here, this is like a piece of filter paper or something, just to give it a background, I suppose. We're going to put the sodium in the water and then observe the result. This is a tiny piece of sodium. There you go, that was it. So, in all three circumstances, did we observe the same thing? And when I say the same, I mean exactly the same. Or did we observe different things? Or better yet, did we observe something that was similar but different given the circumstances because the three experiments aren't really controlled? Which statement is the best description of the science we performed by doing these three experiments? What do you think? We got to vote for similar. Can you explain why you think that they're just similar? And if you're thinking, well, duh, they're similar, yeah. I'm trying to just get you to voice why that is, though. Because obviously they're not entirely identical, but they're also not really unique. What features about them make them not unique? Yeah, there's different reactions under different circumstances, but or slightly different. There we go. That's the word I was looking for. So based on what was going on, we got a reasonable result, but it wasn't identical. Oh, excuse me, my seltzer water there. It wasn't identical. I'm just burping all over the stream here. That's great. Yeah, in fact, the smallest sample caught on fire because its surface area was so small, you could actually see the flames on it. Whereas the bigger ones, they just exploded because the hydrogen gas that was given off eventually detonated. If you are curious what the reaction is for this, just in case you wanted to know. So let me get the pen out here. Can we see it down there? So this is sodium plus water makes sodium hydroxide and hydrogen gas. This is not balanced. There should be a 2 in front of the sodium, in front of everything but the hydrogen gas. But what is really going on for those explosions is that the thing that explodes is the H2. The H2 heats up, and then it detonates with the oxygen in the air, and you get a boom. Because this reacts with oxygen to make water again. Alright, that's just our science little fun minute there. So what... Yeah, they didn't measure the sample. These are all qualitative observations. So what we've observed is that our fact that we can discern about these experiments that are reproducible is that sodium reacts violently when exposed to water. It tends to blow up, it ignites the hydrogen gas, etc. Now, we don't know why this happens. Like, would it explode in a vacuum? That's a good question. The answer to that is actually no. The hydrogen gas can't combust in a vacuum because there'd be nothing for it to react with. You would get hydrogen plus nothing, really. Hydrogen would be the only gas in the vacuum, so it would not detonate. All right, let's talk about scientific laws. Remember how scientific law talks about a broad category of observations? We can do that by examining other elements. Now, if you were to look at a periodic table, you would notice that there are other elements that I've selected on the screen located near sodium, and they have a specific trait in common. I've selected these specifically for this purpose. And I think that the slides I'm using are old because this is going to link to the wrong video, but this potassium one won't. Oops. It loaded the audio in half the video before it even appeared on the screen here. So we're going to put potassium in water. And what our goal here is to say, same question really, is this experiment completely different from the sodium experiment, similar, and has some common things going for it, or are they exactly the same? So here we go. So that's really fast, so I'm going to just do that again for you here. So what are our observations? I'm going to put it back in the middle so that we can get a nice little picture of it, and then I'm going to go to the sodium one and do the same thing. So just by looking at the color, assume there are no camera tricks. These are in the same room. Are these the same experiment? Could you mistake one for the other? What do you think? So the results are similar. And you might be able to mistake them, but are there qualities that you could use to definitively identify them? Like if I play this one again, and I compare it to this one, do you see any obvious differences between them? Anything obvious enough that you could use that as evidence to discern it? Oh, look, I'm a recommended viewing, along with the music I'm playing for you, and the music that I listen to all the time. Yeah, the color is the most obvious giveaway. Oops, I want to pause this here. As far as I'm concerned, for, like, visual appearance. So, like, you could see that the colors are very different. But you can also see that the other reaction, the potassium reaction, was very fast. We put it in there and it immediately starts dancing around. It's faster, it seems more energetic. So there are differences between them. They are similar. But I appreciate your being candid and saying, well, you could mistake them because we only have 2 data points to work with. And that's a really important point here. When we're doing science, we're going to need to establish patterns, but 2 is not a pattern. 2 is just a coincidence right now. So what we're going to need to do now is I actually have to do this. And I got to go to this guy's page and find the other 2 here. Now, see, you remember that because you took 140. Or you've taken a... You've taken 161 and already know quantum mechanics. Rubidium. I can't spell. But if you were introduced to this for the first time... Okay, that's the one I want. And then I want... Oh, wait a second. Hold on. Oh, that was a great frame I paused that on. I kind of wish I had kept it there. I got it the frame that it exploded. There's cesium here. Oh, darn it. I hit the wrong button. Oh my goodness, YouTube. Stop that. Okay. I'm trying to set it up so that I don't spoil the surprise here. Yeah, I hadn't actually hit the button. because I had to fiddle with it a lot, and you're going to see why the video isn't displaying if you remember how fast these go. Because blink and you'll miss it. I hit play and it's over. So this is rubidium. Like, that's it. It's done. And by the time I would have gotten that set up, it would have been over and frustrating to deal with. So we're going to play that again at normal speed. And then at slow motion. And you can see this thing looks round because it's spinning so fast. So that's rubidium. Let's do cesium. Cesium, absolutely blink and you'll miss it. Okay, ready? Here you go. It's done. Like, we have to get super slow-mo here. 2 frames of animation is all it has before it's already detonated. And I just really like that sound it makes. Sounds like an old 8-bit shooter or Atari game or whatever. So we have made an observation, and that observation is that as we go down that group, elements tend to become more reactive, but they react in the same way. They blow up with water. Now, I actually asked this to my 140 students earlier, and one of them suggested that maybe it was because the molecules weigh more. And so I asked, okay, what experiment could we do to disprove that? Because it turns out that weight doesn't affect it. But that's a really good guess, because as you go down the periodic table, all the elements have a number that gets bigger under them. So they must weigh more. Maybe that has to do with it. And that's certainly the first place I would go, because it's right there on the periodic table. But how would you disprove something like that experiment? And this is the part about thinking as a scientist. What could you do to show that it is not the weight that is affecting the reactivity of these? And that instead it has more to do with the column you're working with. Any ideas at all? This is the part of 161 where I had to make you guys think outside the box. Which we're going to do a lot of, by the way. How would you disprove the link between weight and reactivity? Make sure that the weight of sample of metal is part of the control group. So when I say weight, I don't mean the weight of the sample in terms of grams. I actually mean the atomic weight, sorry. Because that's what's on the periodic table. But you're right, that is what you would do to make sure that if I put 5 grams versus 10 grams or whatever, that isn't affecting it. I apologize for being unclear. How would you disprove that the atomic weight has something to do with it? Not quite the bonds. Not quite the answer I'm looking for. So, for instance, let's look at cesium. Cesium's atomic weight is 132. Rubidium's is 85, and potassium is 39. I want to disprove just the weight. Mike, I think you're getting ahead. Like, you're giving the actual correct answer. But I just want to disprove this one. Because you could easily think that, oh, it's the weight, and you need some sort of scientific fact that shows otherwise. So, you use different isotopes. That's a good idea, but it would turn out in that case, you would get the same result. So that could be misleading. So, like, if I weighed cesium 138, it would also explode. And so that might support your idea. Keep thinking. I'll give you a hint. I want to pick something heavier than cesium. What should I pick to disprove that weight has anything to do with it? Not quite where I'm going. Yeah, pick a different element. Let's do gold. I'm going to throw gold in water. Gold is heavier than cesium. It should be even more reactive, right? The example that I was going to do for you, because I have a video, is I want to show you barium in water. So if I put barium in water, barium's right next door to cesium. Should be just as reactive, right? This is what happens when you put barium in water. So this experiment and the gold experiment, if I put gold in water, absolutely nothing happens. That should tell you that, wait a second, weight is the wrong way to look at this. I cannot look at atomic mass. That's not affecting it. So then we would go to Michael's idea, which is, what about electrons? What about bonds and stuff? Are bonds being formed and destroyed? And that's the correct answer. That's where we want to go. So you may find patterns when you are dealing with the scientific method, and those patterns can be wrong. That is just a side effect of how science works. Science does not prove things true. Science only proves things false. And we can only eliminate things. So I could tell you that potassium and calcium don't react similarly because we see that. But I can't tell you that potassium and rubidium react exactly the same for this exact reason. Because there could be some other reason out there we just haven't discovered. It looks like Danger Seltzer. It is definitely Danger Seltzer. Now, the important takeaway for the difference between facts and theories here is that facts are a specific experiment, whereas laws are general. Both of these tell us how matter behaves. Kind of went off the side of the screen there, sorry. Neither of these experiments tells us what exactly is happening, though. And this is where the whole, oh, we're doing a reaction by passing along electrons comes in, which, if you've taken other science classes, you already know what's going on here. If you don't know the nitty-gritty details, that's fine, because we are going to learn that in Chem 161. This is what Chapter 3 is. Chapter 3 talks about this phenomenon. How do I get an electron off of an atom and onto another atom, and then what are the consequences of that? And what is happening here is that I am passing electrons from the metal that I put in there to hydrogen. So that instead of being hydrogen bonded to oxygen, it becomes hydrogen bonded to hydrogen. I'm shuffling around electrons is what's happening here. Now, why do the elements in group 1A react how they did? Why is cesium the most explosive? Why did it go boom the fastest? We're actually going to learn this in Chapter 3, and we're going to come back to that. This is the answer, which none of these words probably make sense to you, unless you've taken other chemistry classes before. But that's okay. What's important here is that in order to discern our scientific theory and deduce why matter behaves how it does, we need a lot of information in detail. And that requires lots and lots of experiments of a very precise matter. So if you ever hear somebody say it's just a theory, that person is dumb. That's my shtick on them being dumb. All right, that's the scientific method. What I'm going to do is I'm going to give you a pair of experiments. And what I want you to do is I'm going to give you 2 minutes to look over these and try and determine which statements in each pair of experiment, or in each, not pair, I'm sorry, each set of information. Experiment A has a fact. Experiment A has a scientific law, and it also has a theory in there. And I want you to tell me which one is which based on these sentences to the best of your ability, okay? Don't try and do, oh, the one that has the most words is clearly the theory, because I've actually set it up so that it's not like that, okay? So look for the one that explains the most about what's going on, and that's your theory. Look for the one that is the most general to a very specific example. That's your fact, and the other one's the law. Okay? All right, good luck. We're all counting on you. I'll be back in 2 minutes. I should be clear. So within this set here of A, one of these statements is the fact, one of them is the law, and one of them is the theory. Which one's which? And then down here in B, one is a fact, one is a law, and one is a theory. Can you match up with what I chose? All right, let's go over the answers here. Now, the way that I do these types of problems is the first thing I want to look for is I want to look for the general idea of what's going on here. And so in experiment A, we're just talking about heat and temperature and stuff like that, right? Okay. Which of these three statements tells me the most about heat or temperature? So looking at this first statement, mixing boiling water and cold water makes a solution that is lukewarm. And that doesn't really tell me anything about why. The final temperature of two objects in thermal contact with one another is their average temperature. That doesn't tell me anything about why. Like, Why is it the average? Why do I get something in the middle? And then the third statement, heat moves through molecular vibrations. That's the important statement. So that would tell me, oh, okay, well, if heat moves between vibrations and everything is vibrating, they'll all eventually vibrate into each other and have the same vibration, which will be the average. So this must be the theory. Of the other two, I want to pick the one that is the most specific. This one right here just says two objects that are touching. This one here tells me about, oh, boiling water and cold water. This is more specific. So the specific nature of this makes it a fact. That is a fact or an observation from one experiment. This is the observation from a bunch of experiments. In fact, what I have indicated with law there, that is just me summarizing what is called Newton's law of cooling. If you have two things that are at temperature A and temperature B, the end temperature will be between them. Now, that does require the objects to be the same material. I'm just not going into that much detail here. All right, let's do the next one here. So again, I'm going to follow the same process. I'm trying to find the theory first, really, in order to get the idea of what the problem is asking me about. And then from the other two, since the other two are similar, I can then discern the law from the fact. So looking at these three statements here, sodium chloride mixed with water is toxic because the high concentration of the solution forces water out of the cells. Seeing the word because is a really good indication that you're looking at a theory. Let's look at the other two, though. A flower will thrive when given distilled water, but wilts when given salt water. That doesn't tell us why. That just tells us what. Vegetables and fruits do not grow well in areas with high concentrations of ions in the soil. That doesn't tell us why, it just tells us what. So, process of elimination. This must be our theory, right here. Because it tells us what's going on. If there's too much salt, then all of the cells crenate. Crenation is when the cells dehydrate, they shrivel up. This can happen in your body if you drink salt water. All of your red blood cells will shrivel up. This changes their topography, which makes them unable to carry oxygen. That's not good. So don't drink salt water, you'll die. The same thing happens if you're diabetic. If you're diabetic, you have too much sugar in your bloodstream, and then you dehydrate, and your blood cells shrivel up. If you have too much sugar in your bloodstream, you will just constantly be peeing because your body is trying to get water out of, or is trying to get water out of you, so that you don't, so that you can clear out those ions, but you end up just getting the water out. I have a friend who recently just got diagnosed as a diabetic, and he's like, oh, I'm drinking water like crazy. I'm just constantly thirsty. And this is that phenomenon. It's osmosis. We'll talk about osmosis in... I don't know when we talk about osmosis. 162 or 163, I think. Now it comes down to the other two. So we've got a flower and vegetables and fruits. Which one's more specific and which one's more generic? The specific one is going to be our fact. And the generic one's going to be our law. That's how I do it. You'll notice that the fact and the law more or less tell you the same thing, but one will be specific and one will be general. The theory just tells you a ton of detail. Find the detailed statement that gives you the most underlying understanding of what's going on, and you're all set. All right, that's our overview of the scientific method. Any questions on that, let me know. Let's just talk really briefly about some domains that we're going to observe in chemistry. We're going to use these terms a little bit, not a ton. Whenever I talk about anything macroscopic, I mean something that we can perceive with our eyes. So in this picture right here, the macroscopic domain would be the iceberg that we're looking at. When I say the microscopic domain, what I actually mean is anything that is at the atomic level. A microscope actually cannot see atoms. They're too small for even that. You need like a tunneling electron microscope for that, and that's very different. So the term micro in this context just means atomic matter. So this would be molecules that are either bonded together through intermolecular forces or independent from each other, or even like a macromolecule, like a carbohydrate or a polymer or something like that. We would draw these structures at the microscopic domain level. We cannot see the microscopic domain well because we don't possess tools to do that, and perhaps we never will. There are some experiments that we can do to get the structure of an atom, and I'll show you a few pictures of what we've got. They're not great because the resolution is low, but it is really neat to see the patterns that are there. We sort of have to play imagination time when it comes to the macroscopic domain. The major point of this class and of a lot of the chemistry classes and also biology is training yourself to be able to visualize what's happening in the microscopic domain, because it's hard to do that. That requires practice. So by looking at all these pictures and by drawing structures and visualizing how they fit together, we're going to do all of our work in the microscopic domain and also the symbolic domain. The symbolic domain is just, let's represent the picture as a word. Associating these two things together is going to be the challenge. This one you've already done. You work in the macroscopic domain all the time. But if this is your first or even second chemistry class, working in the microscopic domain might just be something you've only done for maybe 10 weeks. I've done it for 10 years, and I still have to sit back and think, okay, how does this work? And I visualize the molecules in my head. I spin them around and I move them around and I say, oh, okay, I can see that this works. You won't get there in 10 weeks, but we can certainly get you on the right path to develop that skill. And so that's what we're going to be doing. I think that's all I have time for. I don't have 10 minutes to start the next section, so I'm going to leave it here. We'll do 1.2 through 1.3 tomorrow. Probably a little 1.4. We're going to get to sig figs next week, maybe at the end of Wednesday's lecture. But I'm going to call it a night for tonight, since it is almost 7 p.m. I want to thank everybody for coming out to the first lecture. We will reconvene tomorrow at the same time, 5 p.m., to continue our discussion on lecture number 1. Make sure that you ask me any questions that you might have about any content, either over email, over Discord, on the discussion board, wherever it is, as long as you get that information to me so I can help you. And I will make sure that this video gets into the playlist and link that link in just a little bit. I'm going to then go and answer all the emails. I see that I have some emails. If you've sent me an email between noon and 7 today, I haven't actually gotten to it yet. I'm going to get to it very soon then. Have a wonderful evening, and I will see you tomorrow.